Morning, everyone. Welcome. Welcome to another spring showcase. We're excited to be presenting alongside Northern Ireland Water today, who will be sharing the key learnings, insights, challenges and benefits behind their collaborative work to optimise wastewater treatment centres that are facing unique challenges through innovative nature-based solutions provided by ABS. So a little bit about Spring for those who aren't familiar. We are the Centre of Excellence for Innovation in the UK and Ireland, and our main objective is to enable the effective delivery of innovation and collaboration by creating centralised intelligence for both water companies and suppliers. Our mission is to attract, connect and support innovators across the industry to accelerate transformation. That is why we facilitate and host these knowledge transfer events such as today. Through Spring Knowledge Sharing, we hope to support the transfer of learnings from an innovation project to the wider sector, creating project legacy that helps innovators identify and adopt the right solutions at a greater pace. So last year, we actually partnered with Ofwat, the economic regulator for England and Wales, to build out a view of what best practice knowledge sharing actually looks like. We brought together senior leaders and innovation managers to design a vision for knowledge sharing. And what is it that we're actually trying to achieve? Ultimately, we want to unlock faster pace adoption by creating a world-class knowledge sharing culture. And we created 6 best practice principles to help those and guide those who want to do this. So the first of the principles is to learn from what already exists before committing to innovation projects. So to aid this, we created the Spring platform, which hosts a multitude of project case studies aligned to the priorities laid out in the Water Industry Strategy 2050. Links to these resources will be put in the chat in a moment for anybody who wants to take a look. We are also working on other tools to ensure innovation intelligence is easily accessible to the sector. The second one is to target innovation insights to the right audience to meet our objectives. So we want to make sure the right people are here listening to these lessons. So for today, do we have the relevant people on this call who can actually take action on the knowledge shared today within their own organisations? Number 3 is that insights are regularly shared through multiple channels from day one of the project. So historically, knowledge sharing has always happened at the end of a project, and we really want to start moving towards a model where we share from day one. Number 4 is that the sector knowledge is open and centralised. So we want to make sure that we're all being open and honest when it comes to the knowledge from innovation projects. We want to make sure it's all in one place too, i.e. Spring, because fragmented knowledge, as we know, is much more difficult to engage with and learn from. The 5th one is that insights from both innovation successes and failures are shared, and this one is really key. So as we all know, the lessons learned from failures are just as important as the lessons of successes, and the challenges that are faced along the way are just as important to know about as all of the things that sailed smoothly. So hopefully we'll hear about some of those today from our presenters. Number 6, finally, is that people are empowered to receive and embed lessons from external sources. So Spring and the presenters on this call can all share knowledge, but we want to make sure that the receivers of the knowledge actually have the resources and capacity required to make that change, and that they feel empowered to do so. So back to today, I'd just love to give a warm welcome to all of the audience members joining us live. As always, we will be including a poll during this event to gain your thoughts. Answering our poll is the most impactful way you can help us make sure that these events are providing value to you, your organisation and the wider sector, and that these showcases are supporting faster paced adoption of solutions. Your insights not only help us understand the actions you plan to take from today, but if there was anything more we could have done or shared to ensure successful transfer of the key insights from innovation projects. We'll be launching the poll at the break, so please do make sure to submit your answers when this comes through, if you do need to drop off before the break at all. We'll launch the poll again at the end as well for those who didn't get a chance to answer during the break. You'll also get the chance to ask the project team any questions at the end of the session, so do make sure to keep putting your queries in the chat throughout today's presentation. So on to today's session, I am just going to quickly run through the agenda, talk you through our speakers, and then I'll hand over to Paul. So we'll start with hearing from Paul Davison on the challenges that Northern Ireland Water are facing strategically, and a bit about the partnership with ABS. We'll then go into some more context setting from John Griffin, followed by information on ABS, biofermentation, and the benefits seen so far from Rob and Connor. Then we'll have a quick break, and then coming back from the break, we'll go into some lessons learned as a panel discussion, followed by a questions and answer session to close. So just to reiterate, we'll be joined by Paul Davison, Head of Wastewater Strategy, John Griffin, Head of Wastewater Infrastructure, Rob Whiteman, PhD, who is Technical Director of ABS, Connor Hughes, UK Field Services, Dermot McCurdy, who is a Northern Ireland Water consultant, and Kyle Gerald and Michael Clay, some USA customers that ABS have worked with historically, and we'll be hearing from them about the impacts ABS has had in their respective cities. So to finish up, I'll now hand over to Paul. If you could pop your camera and mic on for us, please.
Okay, thank you, Leah. So Leah, I'm not seeing actually any slides at the minute. Is there an issue or?
Oh, are you not?
Sorry, I'm just seeing the title slide. I'm actually not seeing any of my slides.
Oh, has it not moved around, has it?
Let's just see if I can.
Do you want this slide?
Okay, I can see my slides now just by moving myself. Anyway, sorry. Okay, good afternoon, everyone, and my name is Paul Davison from Northern Ireland Water. I'm Head of Wastewater Strategy. And I suppose where we're coming from here is the major challenges that our industry is being hit with, economically, politically, and environmentally. And if we continue the way we've always done it, we will always just get what we've always got. So we have to think outside the box, and we need a paradigm shift, I think, in our industry to be able to deal with all of these political, economic, and environmental challenges that we're having. So next slide, Leah. So Northern Ireland Water is a wholly owned company owned by the government. It has a 6-year investment plan, very similar to the investment plans in England and Wales. And at the minute, we're going through our PC21 plan, which is a 2.2 billion plan investment in water and wastewater infrastructure. And all of our funding is coming via government. So we have no water charges. So we face very significant challenges from wastewater treatment, capacity, and also addressing environmental needs. And our ultimate objective here is to be able to improve the service while maintaining efficiency and delivering on the performance commitments. Say next slide. So in terms of wastewater treatment, we're looking for compliance within the regulatory water consent, and that's mainly sanitary, but also bringing in flow compliance into that as well. We also then have got a capacity issue that a number of our treatment works are over their headroom, and there's to meet growth, these works then are overloaded. We are limited in terms of capital expenditure, CapEx, and we're also constrained in terms of our OpEx, also our operational costs. We also then have very challenging carbon footprint challenges as well. And also we're looking to see, can we reduce the transportation and disposal of sludge from our wastewater treatment works, as one of our incinerators is coming near the end of its working life. Okay, next slide. So the knowledge sharing that we would like to try and achieve here is to be involved in new and innovative processes in the industry to be able to meet the challenges and the constraints going forward. In the past, and we're presently doing this here, we're optimizing the physical aspects of a wastewater treatment works, and we have saw some benefits from that. What we're looking now, we're working with the ABS team, can we optimize the biology of a wastewater treatment works and then see then further improvements in the performance of that asset. And the ABS team, they will be able to give more details on how they've been able to achieve that working with Northern Ireland Water. Next slide. Okay, so One of the areas that we've been working with ABS is on our sludge production, and maybe Northern Ireland Water is slightly different to the rest of kind of the UK, is that we don't do any biomethane production, so no anaerobic digesters in any of our facilities. All of our sludge is thickened, dewatered, transported to two incinerators in Belfast, where it is burned. So we're looking to see, is there any way that we can reduce the quantity of sludge that we're producing, so we've got less cost in terms of the dewatering, thickening, less transport costs, and then less combustion costs of burning that waste as well. So through the SBRI initiative, that's a small business research initiative, we've been able to then tap into some of these ideas. And ABS were successful in completing the stage 1 of that approach and have demonstrated very positive results in terms of sludge reduction, and we are in the process of seeking to get further investment to then take this here to stage 2 implementation. I think that's the end of my slides, and now I'll hand over to John Griffin, who will then go into more detail on some of the work that we've done with ABS in the past.
Thank you, Paul. Thank you, Paul. I'm John Griffin, and I'm currently one of the project sponsors in Northern Ireland Water, responsible at the moment for sewage and wastewater pumping station upgrades. However, in a previous role, I was responsible for managing Dungannon Wastewater Treatment Works emergency measures, which was our first experience of working with ABS and of biofermentation in particular. I was also the project manager for the Biofermentation pilot project. Next slide, please. Dungannon Wastewater Treatment Works was designed for an original population of 65,000, and approximately 60% of its influent is from trade sources. In fact, the largest trader on their own accounts for over 30% of the plant's loading. The three largest traders are all meat producers. So as you can expect, this can have a significant impact on the loading of the plant, even though they have pre-treatment. It was during Christmas 2016 that the works suffered a significant toxic shock, which resulted in a loss of secondary treatment. And as a result of that, we needed to bring in significant numbers of seed sludge in order to bring the works back into compliance. But we always continued to struggle with ammonia. In order to bring the works back online, we looked at a plethora of options, one of which was biofermentation. Ultimately, we knew we needed to provide significant additional secondary treatment, and we decided that Nerita was our preferred solution for the long term. So we brought ABS on board with an 18-month contract to provide us with biofermentation. And during that period, we did not bring any additional seed sludge in from other sites, and we were able to return the works to compliance, particularly with ammonia. Next slide, please. The trial at Dungannon was part of a significant number of changes which all occurred at the same time. But we needed to do all of them to bring the works into compliance. We knew that biofermentation had contributed something to turning the works around, but we did not know the extent. So therefore, seeing the potential for this technology, we conducted a full pilot project, and we selected 5 sites. Oma was an activated sludge plant, which is having sludge management problems due to imports. Moy, an oxidation ditch with no storm management, but similar to Dungannon, had significant trade loading. In this case, it was coming from apple processing. Killygonnan was a packet duration plant with no storm management and suffering from high infiltration. 5 Maltine, rotating biological contactor, which suffered from rogue trade that had very high biological content. And lastly, Limavady, which was a relatively new plant and did not have any issues, and it was our base site, our control works. However, there was maintenance carried out on one of the lanes whenever we were completing the project. Next slide, please. We noticed a significant improvement across all sites. We noticed the Killy-Gonlin was still subject to high flows, but its recovery was a lot faster after washout than what it would have been without biofermentation. 5 mile time was our biggest surprise. Biofermentation provided an unequivocal improvement on the performance of the works. Overall, we noticed improved compliance, more resilience. We had works that could recover quicker from shock loads. We used less power. We had less sludge production and less chemical use. And overall, we noticed that the effluent on all of the sites was excellent, and that the biological performance was to a nitrification quality. Next slide, please. As it was a pilot project, a report was produced, and that report was signed off by the head of scientific services within Wastewater in Northern Ireland and myself. We wouldn't have put our names to it if we wouldn't be happy to endorse it. And we are very happy to share it with other companies within the UK and water industry. But going forward, we know we need to do a trial at a larger works. We need to get more data so that we can do a more detailed cost benefit analysis to work out the economics. Both of the projects that we did were provided under CapEx with no OpEx. We need to come to working out a methodology which is available for CapEx to provide the plant and ensure that we've got the operational capital to be able to run it. Thank you very much for listening to me, and I'll now hand over to Rob and Connor.
Good afternoon, everybody in the UK. My name is Rob Whiteman. I'm the Technical Director of ABS, and I want to thank Connor Hughes, our Field Services UK Manager, for the input into this presentation. And let me put my camera on there. So we'll start off. This is going to be a complete paradigm shift in thinking. Like Paul has said, I guess the UK water industry is looking for some way of trying to transition out of doing the same things over and over again. And we're going to focus on how to optimize the biology, or how we develop this technology to optimize the biology, which probably in the last 115 years has really not been done. I want to thank our team members, Northern Ireland Water, City of Dublin, Michael Clay, and Kyle Geralds, formerly from Stark, for joining us on this call and supporting our efforts to put out this education. So we're going to talk about sustainable nature-based solutions. I'm going to go through the technology, then I'll go through some case studies around compliance, capacity, energy, sludge, carbon footprint, and then we'll talk about some of the benefits and go into the break. So, okay, there we go. So if we look at the evolution of nature-based technology, freeze-dried bugs have been around for a long time. These generally come in a bucket, but it's almost, in terms of the evolutionary scale, like being the monkey. Leah, it's not transitioning through, it's just moving the slide ahead.
1 second, let me take a look for you.
There we go.
There you go.
Okay.
If you want to take control back from me and try again.
Yeah. Okay, there we go. Okay, so basically 1990, after I was came to the United States, we developed a pre-acclimation device using the freeze-dried microbes because the plants over here were 10 times the size of what we find in the UK. And so we had to have some way of getting greater impact. And this had some partial effect. But at the end of the day, the percent actives in the freeze-dry material are usually about 1%. And we would end up with contamination from other bacteria. I'm trying again, Lou. Can you? Oh, there we go. I've just got to click on the slide, I think. Eventually, around 2000, we were troubleshooting a plant that was suffering from filamentous bulking in the pulp and paper industry, and biofermentation was born. What this does is grow the microbes on site, being able to deliver 100% actives, full performance. We can make custom blends, grow any microbe, and it provides controlled fermentation, allowing us to deliver 10,000 times more than previously possible into the existing plant. And this has allowed us to now create a microbial population shift in the biology, which has created a paradigm shift in our thinking. So if we look at the generations in the last 25 years, you may have noticed in the top right, we are celebrating 25 years of successful innovation in technology. We started out in industrial, filing our first patents on the process, and we were able to get compliance within 10 days on plants treating 160 megaliters a day, in English terms, 40 million gallons a day for Americans. The second generation was around 2007, 2008. We started exploring the municipal sector in the United States to control filamentous, and we noticed reduced sludge production. And that's when we first went to the city of Dublin and started working with them. The third generation, we worked with Carl Gerals at Stark, where we'd already demonstrated sludge reduction in the aeration basin, and we were getting results of 60 to 70% reduction. And Carl asked us, could we work in his aerobic digester? And we said, we don't know. And we tried it and it worked. And Carl went about 5 years without hauling sludge. And we have another client that's gone 6 years now. Then the fourth generation, in the last couple of years, we developed the accelerated simulation test, which can demonstrate improved settlability, and I'll show you an example of that, and expanded our patent portfolio. So that is the generations of biofermentation over the last 25 years. So why would you grow organisms on the outside of a plant and not try to grow them on the inside? Well, if you look at environmental engineering, the whole basis of our training in environmental engineering is to grow the microbiology in situ. And this creates a disconnect between environmental engineering and microbiology. Basically, in situ growth, we drive the mass, so we increase the mass through increased activity. This creates undesirable byproducts, poor settlability, because as we drive the mass, we increase our solids retention time or mean cell residence time. By growing the microbes ex situ, we can deliver a huge amount of viability of non-pathogenic bacteria, which allows us to drive flock structure, non-filamentous material, improve settlability, and improve activity. And again, mass is not necessarily driving viability. It is simply driving activity by increasing the mass. So we're actually able to get a lot more activity by driving viability of the biomass. So why do we need probiotics? Bottom left, we see Eichel Boom, who was one of the people that really started to study the microbiology on the scope and came up with a filamentous ID grid. And this was followed by David Jenkins in the United States, who also did the same over here. And what we see in that slide is basically pore, open, weak flock structure with some filaments. And basically, this leads to poor settlability and operational challenges in a system. So this leads to high SVI, settle volume index, which can be greater than 120, poor settlability, no compaction, high effluent turbidity, and basically compromised compliance because we have small fines going out in the effluent. So how does it limit the operation? Basically, poor sellability. The operator has a choice. He can either lower his mixed liquor so that he can get better sellability because there's less solids in solution, or as environmental engineers, we would look at the system and say, well, it doesn't have enough clarifier capacity. Let's build some more clarifiers, and that adds CapEx and OpEx. And by the way, when the operator lowers his mixed liquor, he's creating higher OpEx because we're wasting more out of the existing plant. The alternative solution is to look at using probiotics to create a microbial population share, allowing a longer mean cell residence time. So reason 2 is inhibition by chemicals that prevents growth of key microbes. And we see Arden Lockett there in that picture, who discovered activated sludge in 1914 in Manchester. And since that time, we didn't used to have antibiotics in those days, pre-1930. And the golden age of antibiotics was 1950 to 1960. And what we've seen is an increase in antibiotic resistance and pathogens in our sludge since the onset of antibiotics. The other thing is cleaners and household detergents weren't around before the 1930s. And since COVID, hand sanitizers have come in. So if you go back to the original paper of Arden Lockett, they actually talk about sieving the sludge through a metal sieve, not through a 1.5 micron or filter paper, which indicates that the sludge size was probably quite a bit bigger. And I think that over the last 100 years, if we had the data, we find that the sellability and floc structure has been seriously compromised by the kind of wastewater that we now have. And of course, all these are now becoming emerging contaminants of concern. Reason 3, aging of the sludge decreases the viability. It's like making old people's home. Here on the left, we see trailers that typically our biofermentation units come in, and these are called Model 1500s. On the right is the typical floc structure. And if we consider that viable organisms sit on the top, then as we add microorganisms to the system, single cell microorganisms, they get absorbed onto the surface, and this increases the viability and hence the activity. So what is the impact on activated sludge? Well, we put the biofermentation system online as a full turnkey service. First thing we're going to see is improved settleability and compaction and a reduction in the filamentous. The impact of that is to improve the effluent quality, as John talked about, that he's seen in his projects in Northern Ireland, ensuring compliance. Third thing is, if the operator wishes, he can then start to increase his mass to increase his process capacity. And then the fourth thing is, the better settling sludge, the more hydraulics you can get through the works, and particularly a secondary treatment system, assuming there's no piping limitations. Then you see improved dewaterability, reduced polymer usage. You see a reduction in the amount of solids produced, usually by about 30% if it's not optimized, up to 60 or 70%, and the operator controls that process. Finally, we have also noticed about a 25% reduction in electrical usage where VFDs and diffused air are used. And then finally, what we mentioned earlier, development of the process of advanced digestion to continue digesting the sludge further. And we've seen the ability to reduce the sludge mate by 90% and also make what's called a Class A or AA biosolids in the United States, which is a low pathogen sludge. And then finally, what it was developed for originally, which was rapid recovery from toxic shock. And you can't separate out any of these benefits. If the technology is applied, you get all of these benefits by optimizing the biology. So if we look at the mass balance for a plant that's doing 95% BOD removal, for every 100 kilos of BOD going in, you provide nitrogen, phosphorus, oxygen, and biomass to start the reaction. We get about 60 kilos of excess biomass from that plant, 5 kilos in the effluent, the rest goes to CO2. If we use ex situ growth we see that drop to about 20 kilos of excess biomass, less than 5 kilos of effluent BOD, with the balance going to carbon dioxide. So why would we even consider this process? Well, pollution prevention hierarchy by DEFRA or EPA, they're both the same, with respect to sludge disposal, requires us as environmental stewards to look at source reduction. However, the industry has been very focused on disposal methods, landfill, pelletization, incineration, volume and mass reduction through aerobic or anaerobic digestion, energy recovery through anaerobic digestion, and beneficial reuse on land application. But biofermentation is really the only point source reduction technology, which is what we call it. And that is the basis of sustainability for any kind of program moving forward. We have to look at source reduction technology. In terms of the evidence of cause and effects of probiotics on waste treatment plant, this is part of a 5-year study from Port St. Lucie. The blue dots are before and the black dots are during the use of the probiotics. And this is food to microorganism ratio on the x-axis versus kilos of sludge produced per kilo of BOD removed to normalize the data. And you see that doesn't matter where we operate on the F2M curve, because a lot of engineers criticized us because we would increase the mixed liquor. And so they argued we would change the F2M and therefore not really reducing biosludge make. If you look at the data, we determined that that was not true during the study. And if you look at the R squared around the fitted curve onto these graphs, and R squared means how closely it fits to that curve. With biofermentation, we had an R squared shift to 0.96, which I'd never seen in wastewater. That basically means you can rely on the fitted curve plus or minus 4% or so in your accuracy, which allows engineers to design things more accurately than whereas the blue dots before, the accuracy was only about 0.45, which would be about plus or minus 55%. And sludge reduction occurred irrespective of the actual F2M. And we've seen since that biofermentation always improves the R squared. So if we look at classical sludge processing and the net zero carbon challenge for the UK, and a lot of plants have primary sludge make, etc. And sludge production, as mentioned earlier, is 0.6 kilos per kilo BOD removed. Although I noticed I've still got pounds in here. We have all sorts of methods of decreasing that mass initially, either through anaerobic digestion, aerobic digestion. Problems with anaerobic digestion is we're finding we get return filtrate that's high in ammonia and phosphorus back to the front end of the plant, and then we have to treat that all over again. We're recovering about 50% of the methane in terms of energy recovery before we go to volume reduction using either presses or centrifuges. And then if we look at disposal methods, we have options of land application, landfill, which is certainly very expensive in the United States. I'm sure it's very expensive in the UK. Incineration, which is costly in terms of capital. And we're looking heavily here at composting and pelletization to sell sludge into the consumer market. But the reality is there's so much sludge to be dealt with, not all these disposal methods can handle it. And each one of them, as we go forth into incineration, etc., all increase the carbon footprint and all increase the cost. So with a paradigm shift in thinking, what happens if we took the ultimate system and optimized the biology? First of all, we would probably convert the primary clarifiers to anoxic or anaerobic zones so we could get total nitrogen removal. We would treat the aeration basin going to 0.2 instead of 0.6 pounds or kilos, whichever you want, per kilo or pound of BOD removed. That would have a serious effect on all the downstream processing equipment and requirement for that. And if we added advanced digestion, where we could actually get a net 10% residual by removing 90% of the sludge completely, incineration would become a lot more cost effective. And in fact, this whole process would decrease the carbon footprint while providing the lowest cost alternative to handling sludge. So how do probiotics help the engineer? Well, basically, it's enabling technology, allowing a process shift in the microbial population that's not been possible before, which results in reducing cost. Basically, the biology has been unpredictable and unreliable, and we've used management control tools such as engineering design, operational changes, environmental drivers, or mechanical upgrades to try to control the biology in the past. But now with this technology, it's possible to optimize the biology and shift it to a not optimized place where we can really just get more out of the works and sweat the assets, which I know has been a big thing in the UK. But this creates a paradigm shift in our thinking and the way that we approach wastewater treatment and the way that we look at trying to solve problems. Determining performance, financial benefits, the way that we work is we normally present the technology. We'll do a risk assessment that includes biomass health, data analysis of operational data to ensure valid baseline data isn't available, financial evaluation ensuring financial benefits are going to be there. And with this accelerated simulation test that I'll show you in a few minutes, demonstrating improvement in settleability with activated sludge plants. And another key component during the risk assessment is onboarding operations and defining the operational limitations up front so that we can all work together to optimize the plant and its performance. Then we respond to tenders, agree on criteria. Then we implement full-scale operations on a full turnkey service basis for 12 months, bringing in demonstration equipment. And then we can provide an ongoing service through permanent installations where required. Let me just show you this. This is our advanced accelerated simulation test. This is an example from Dunmurray. And while that's just settling, on the left is the treated, on the right is the untreated. Basically, we have dosed the one on the left with the probiotics. The untreated is undosed, and what we see is about a 37% improvement in the sludge volume index. But more importantly, is if you look at peak settling rate, we actually improve the peak settling rate by about 70%. And this is just a batch test that we've done to try to simulate something without actually having to go to the field with very expensive equipment and putting a lot of personnel in place to run the project. So if we look at the flock on the scope from this test, if you look at the untreated, it had filaments, weak flock, and small flock. After treatment, you see the flock is much more dense and compact, and this allows that settling that you've just seen improvement to take place by improving that flock structure. So what are the applications that we're looking at in municipal? Basically, improve compliance. We believe that this can all be done in 90 days of starting a project. Increased headroom, 25% or so, allowing more hydraulic throughput capacity as well, maybe in the region of 50%. Reduced sludge production, up to 60%. Reduced energy usage and carbon footprint, reduced total nitrogen. We're working on that right now, and we have a number of case studies showing reduced total nitrogen here. We've also worked on algae control, and our future applications include biological phosphorus removal. We're also working on simultaneous nitrification, denitrification at present, and potentially biofertilizers. How's this thing scaled? Basically, because we provide it as a no-hassle, full turnkey service, the client enjoys the results. The scaling is not really a problem. We currently have 3 units in the UK capable of treating between 300 and 800,000 PE. We're looking to assign one of these units per water company. Delivery can be within 4 weeks. We just require utilities, 400 volt, 3-phase, around 100 amp. And depending on how much we're dosing, 20,000 liters a day. We need a footprint, obviously, to put a container, as most of the units there are containerized, apart from one which is still trailerized. And then we can get results in 30 to 90 days after the initial inoculation, which can take anywhere between 2 to 4 weeks. And if additional equipment is required, we can look at lead times at that point. But frankly, scaling a water PLC across its whole region would probably take maybe 5 years, I would think, at the outside, to 6 years, somewhere in that kind of range. We are seeking water PLC partners for the off-watt transform to scale up and get more cost benefit data around the technology. With that, I will go into the next section, which is talking about some of the data that we've received, and I'll do it by section. So this is on compliance. We have rapid compliance with long-term resilience. We believe that we can probably put 90% of the plants back in compliance in 90 days. That's quite a claim, but we have the data to back it up. I'm going to show one example outside the municipal sector. This is from the pulp and paper industry, where we started, simply because this shows rapid compliance. Pulp and paper mills often have toxicity. In this particular case, we weren't adding any nutrient, so the growth in situ was only dependent on what we added to the system. There was toxicity, and it had limited aeration and hydraulic retention time. Both were compromised by about 40%. And this shows one-day BODs. We mobilized our Model 1500 trailer, and upon dosing, we started to see a rapid decline in the final effluent BOD1s going out, with about a 67% improvement over that period of time. This allowed the mill not have to shut down its operation in order to maintain compliance, which is a very big deal for industrial plants. But this is one of the best examples we've got of rapid recovery. It literally can happen immediately. If we now go to the Dungannon data, which was mentioned earlier by John, 65,000 PE. He gave quite a bit of background on this and the problems that Northern Ireland was having, including rogue industrial discharges. They were having to reseed. If we look at before and after, we see the flows increased about 1%, BODs 8, TSS was 6% lower, ammonia 14% lower, and phosphorus down a little bit. And that was because of some of the work that the inspectors were doing on the industrial discharges that helped some of that influent load. Even with that, we saw a major reduction in the effluent BOD of about 56%. Suspended solids were down 56%. We saw a massive drop in ammonia of around about 88%, and that's because we could keep the sludge in the system. And phosphorus actually went down by 58%, and the actual use of ferric usage went down by about 33% of this particular plant. There are a lot of other things. I could probably talk for about another 30 minutes on the other things that happened here, but I just want to give you some high-level data in this particular presentation. So they also stopped hauling sludge in from Belfast to reseed. If we look at capacity, sweating the assets, we'll feel confident that the capacity could take 50% more hydraulics through the same plant if we can improve settleability substantially, which we showed through the accelerated stimulation test. And once we can improve settleability, we can increase organic capacity by being able to hold some more sludge. This is from what John described as their control plant in the second study, with a population equivalent of about 16,200 and so. The flow was about the same, but during the period of treatment, The BOD actually increased by about 40%. We think that people were staying at home more because of COVID. What we see in this particular case, and this was an oxidation ditch dual train with 2 clarifiers, no primaries. We see the effluent BOD going down 33% on average, suspended solids 25%, and ammonia 27%. These are actually in milligram per liters, and the ones I'll show you later on some of the other plants are in kilograms a day. But we did a statistical analysis to look at the standard deviation and the final effluent before and after. And what we see in every case, and this is not isolated, we've seen it on all our other data too, is an improvement in the standard deviation of the final effluent. What does that mean? What that means is that it gives you more reliable effluent quality. There are less flyers. So that means that your BOD is more consistently in permit and your TSS and your ammonia than it would be without the use of probiotics. If we look at 5 Mile Town, which was an RBC, this had a population of about 2,800. There were 4 RBCs here. It had a discharge from a bakery that was loaded with fats, oils, and grease. What we see over the treated and untreated periods is a 47% reduction in the BOD, 48% in suspended solids, and 38% in ammonia. And again, we see a significant improvement in that standard deviation highlighted in green, the top of the table on the right, showing much more stable effluent quality. Visually, this can be seen on the RBC disc very, very easily. Before we started, it was gray and anemic, covered in fat, oils, and grease, and the biology is basically suffocated by this. By introducing new biology, we're able to get the biodisc back to a healthy brown color. When we pull out, and everybody always asks us, what happens when we pull out? It returns to its normal state, which is what it was before we were in the probiotics. They get washed out. And you see how at the last period there on the last slide or photograph, that is gone back to being gray again. But even on an RBC, we see sludge reduction of about 12%. What have we done on reducing energy? Aeration typically goes down about 25% with a variable frequency drive. There's also downstream reduction in energy usage for recycling and processing of sludge, but we have yet to measure that. This again is from Limavady, and the data supplied there. We saw a 25% reduction in energy, despite some slides that I'll show you later where we actually saw a 44% reduction in sludge. So we're reducing sludge in the aeration basin while also reducing energy usage. And that's because we believe we're actually transferring more oxygen solution. So typically air is 21% oxygen. Off gases are typically 18%. Again, this is something we want to measure in our next round of studies, but we believe that we're getting probably 16 or 17% off gas, which would be almost doubling the transfer efficiency into the water. Chemical reduction, important for reducing OPEX. I'm going to show you some data here from the City of Dublin, courtesy of Michael Clay, who's on the call today. And we thank Michael for his participation here and also the support that he has given ABS over the years since 2008. We've been at that plant now for 17 years. And we started just with the goal of reducing the alum usage. The plant is has primary clarifiers, trickling filters, followed by an anaerobic digester to handle sludge, followed by belt process and disposal to landfill. The plant was a recycled water plant, and it was struggling to meet its NTU requirements and had become what Michael calls as alum addicted. Alum dropped off significantly within days and was eliminated within about 45 days or so. And the financial benefits of that to the city were around 80,000 a year back in 2008. And this allowed them to pay for the biofermentation program. And feel free to use Michael's QR code there to listen to his testimony. Smaller carbon footprint. I was asked to touch on this because we really do affect carbon footprint. There is a tremendous amount to talk about. We thank Northern Ireland Water for the modeling of Paul Davison and a number of other people that were involved in the paper that they wrote. And we thank AECOM, formerly URS, for helping us build a model around the ABS equipment so that we could look at this. Okay, how do I go back? There we go. And I want to thank Connor Hughes for actually putting this work together. So if we looked at the impact of biofermentation increasing the capacity of a plant that was 14,500 PE and using the model that Paul Davison and Patty Brow had developed along with a lady from university, I think called Smythe, then what we would see is that if we can increase that capacity 25% without pouring concrete, then in fact we get a net gain in embodied carbon footprint. The carbon footprint of the biofermentation system itself is very, very small, about 1.84 versus several thousand, 2,400 for putting in a new system. The operational carbon footprint is about 0.17. And it reduces the carbon footprint by reducing the sludge make. And so you go from 300 and something on a standard conventional plant to about 225, including all the equipment and everything that we have to put in. And so if you look at the embodied carbon footprint of biofermentation of technology, it's about 1,000th to a 10,000th of a conventional engineering solution. And if you look at the operating carbon footprint, it's about 2 to 3 magnitudes less than conventional solutions. So this really has a large impact on carbon footprint. We have yet to do any cost benefit analysis on this. And I know that carbon charges have come and gone in the UK and maybe are coming back in. I haven't kept my finger on the pulse there. But I think moving towards the 2032 goals of net zero carbon, that this technology could certainly lend its weight in that respect. Looking at reducing sludge production, essentially at a high level, there are 3 phases. One is 30% reduction, which is unoptimized, where really the operator doesn't change anything in the operation of the plant. The other is 60% through optimization, where the operator would increase his mix liquor as the settleability increased, reduces return rates, and take advantage of that improved settleability within the capacity of his system. And then finally, where you could couple this with the advanced digestion process we've now developed to get actually a 90% reduction. So if we look at an unoptimized situation, this was at Limavady again, we see around about a 44% reduction here with no additional equipment and no additional energy. That's really important. So we didn't do anything, but just add probiotics to the waste treatment plant to improve its performance. If we go to the city of Dublin, this wasn't the original goal. Our original goal was to reduce alum, but over the last 17 years, we have seen a 70% reduction on average in the amount of sludge that's being hauled out of there. And that's with BODs actually being about 15% higher right now. And so this is one of the side benefits that I mentioned. Whether you use biofermentation for compliance, increased capacity, you are going to get other benefits as well. And then coming to the work that we thank Carl for at the city of Stark. We started there in 2016. And this basically shows period 1 is when the city was actually hauling liquid sludge pre-2010, and the data from that per kilo or pound of BOD removed. And then we see the maroon bar, which is when they installed a process called BCR to try to get a Class A sludge so it could be disposed of to land, which basically reduces the pathogen content using chemicals by swinging it between a high and low pH. Kyle experienced operational issues with that, and we were called in through a series of relationships. His operator had worked with us before and asked Kyle to talk to us. He kindly did. And 2016, June, we started biofermentation. And over a 5-year period, we saw a 50 to 70% reduction in the amount of sludge coming from the aeration basin, depending on whether you compare it to liquid hauling or the BCR process, which actually apparently increased the sludge make, and probably because they required a RAS concentration of about 7,000 to go to their equipment because of some limitations there. If we then look at, and this again was done without any additional energy or equipment, reduction in sludge. If we then go, Carl asked us at the end of the first year, could we possibly continue the process in his digester? And I said to him, I have no clue. It's never been done before. And we worked together and started the process on his aerobic digester, dosing every month or was as required when the viability dropped. And we took it in and out of anoxic and aerobic states to get rid of the nitrogen content. And we successfully went 5 years without hauling any sludge, apart from one time I think he had to haul some sludge because he had to do grit removal on his aeration tanks. And I believe they just put that to the old drying beds because there was no rush to get it out of there. But there was no continuous hauling. I think this represents around about a 90% reduction. And no disposal in 5 years. Actually used less energy because we only had the aerators on probably 4 days a week instead of 7 days a week, and no additional equipment. And again, Carl's video clip is there if you want to listen to what he's got to say about it. We also looked at the option because in Florida, again, we require low pathogen sludges, preferably, and Class A sludges, and we were able to meet the low pathogen sludge with low fecal, salmonella, enteric virus, and helminth over by using this advanced digestion process. And that will, again, is no additional equipment, no additional energy. And as one lady asked me at the International Water Association conference in Beijing last year, well, what process did you use? I said, we didn't use a process. We used microbial population shift and probiotics. And she looked very confused because she couldn't understand how we could eliminate pathogens through microbial population shifts without a sterilization process. So what does the technology do? Again, it's one technology providing multiple solutions. It improves plant performance, better settleability, hydraulic capacity, organic capacity, reduces sludge production, advanced digestion can take that further to 90%. It reduces your energy usage, carbon footprint, and it provides the operator with much more control. So in essence, without equipment, because ABS provides a full turnkey service, there are no dollars there or pounds. It reduces the OPEX and can be self-financing, particularly if you compare it against the alternatives analysis, which is what we encourage companies to do. And then lower energy requirements, moving you towards a smaller carbon footprint, and eventually, of course, the smaller carbon footprint. At this point, I'll hand back to Leah and try not to press the wrong button. I won't do anything.
Definitely don't press the stop sharing button. Thank you, Rob. And thank you so much for all of our presenters so far for such a informative and open presentation. It's been really, really great. We are just going to go into a very quick 10-minute break before we come back to hear in more detail about some of the learnings and challenges from this project, and then go into our Q&A session to finish off. Do keep putting your questions in the chat throughout the break, and don't jump off just yet because we're not quite done. And for the break as well, you've already got your camera and mics off, so there's no need to leave the call. You can just go and do your thing and come back at 10 past. We are going to be putting a poll in the chat now. For anybody who needs to jump off now, can you please make sure to leave an answer on the poll for us, just so we can get your opinions that really do help us shape these showcases. With that being said, it's now 1 minute past 3, so we'll come back at 11 minutes past 3 to continue with the rest of the session. Thanks, everyone. Okay, great. So that brings us to 11 minutes past 3 and the beginning of our learnings and challenges section, followed by the Q&A. So if all the presenters could just pop their cameras and mics on for this piece, please. Thanks, Rob.
Okay.
Perfect. Michael, Kyle, Paul, if you're still with us, if you could pop your cameras and mics on, and you two as well, Connor. Perfect. Hi, everyone. Oh, Kyle, you've got a little bit of background noise going on, so I'm just going to mute you again. Perfect. Okay, so we'll make a start on the learning section. So I'll just move the slide across. Rob, take it away.
Okay. Did you put the slide up? I don't see it.
Yeah, you should be able to see the slide if you oh, hang on a second. There we go.
There we go. Okay. Do you want me to just talk about each individual part that we put on here? Yeah.
Yeah,
Okay,
absolutely. If you just go through and everyone can add in their thoughts as you go.
Okay. So you know, with any controlled experiment, data validity is very important, and this has been a real challenge to proving out cause and effect, despite the fact that we've done many cause and effect. But over the last 25 years, we've learned that data validity and plugging the holes where required to set and measure KPIs is probably the most important thing in terms of demonstrating cause and effect. And as everybody knows, with wastewater treatment, there's always something happens in the operation that people can point to that says, well, this happened, so it might have been this instead. So data validity and plugging the holes is very important. Defining the project goals clearly, probably not just limited to this particular technology, and also measuring the other potential benefits, because this is one technology providing multiple solutions. Just like the sludge reduction, we never expected to see that, but we were measuring, and so we noticed it, and then we pursued it as an application. Onboarding of operations and scientific services for full optimization. As we provide a full turnkey service, we are doing all the manufacturing of the microbes directly and applying them to the treatment system on a pre-programmed basis and making adjustments if necessary. However, in terms of operations, it's important that they understand that they take the opportunity to take advantage of the improved settleability, reducing RAS rates and potentially increasing solids retention times. So it's important to get them comfortable with how the technology is working. They don't have to understand the technology really. They have to understand the benefits in order to start to operate their plant at full optimization. Cost benefits, as John Griffin and Paul had mentioned earlier, I think getting down to the granularity, because we touch so many areas, whether it be carbon footprint, energy, sludge, etc., and also looking at the alternatives, not just saying, well, this costs this and that costs that. This is an OPEX expend. Let's ignore the fact that we've got to upgrade a plant at a cost of £20 million. No, you can't ignore that. You've got to put it all into the equation. Risk reduction. We've done this now. We realized that there was a gap between us making a presentation and case studies and all the rest of it, and actually getting the client to a point where they were comfortable to apply this in the field. And I think that the accelerated simulation test has really bridged that gap a lot, and I've received a lot of positive feedback on that. Education again. It's very important to continue to educate the client to a level of willingness to accept the paradigm shifting thinking is a change in thinking, and it all takes time. Any culture change in an organization, and Paul can probably lend something to this, it just takes time. And then finally, commercialization. I really think that we kind of got stuck in an innovations box in the UK when we are already fully commercialized and have been for a long time. And everybody likes to say, well, my biological waste treatment plant is different. They're all biology, and the microbe doesn't really care whether it's on an RBC or in an activated sludge plant, and whether it's pure oxygen injection, diffused air, or surface aeration. It doesn't know. It's just receiving oxygen, and it goes to work. And so, and all the factors regarding hand sanitizers, cleaners, antibiotics, all present in every single wastewater. So I think getting stuck in the innovations box has been a problem, and we're working on scaling up right now in the UK and both in the US. We're talking seriously right now with a plant in the region of 400 megaliters a day or 100 million gallons a day. So that's what I feel are our main lessons learned.
Great. Does anybody have any other thoughts that they would like to add to that at all? Any particular challenges that you encountered in your own organizations when implementing biofermentation, and how you overcame them? Perfect. Okay. In that case, I think if it's okay with you, Rob, we can move forward into the Q&A section.
Sure, go ahead.
What about our
Perfect.
two guys in the States? Are they good to speak?
Great. Apologies as well to those in the audience. There's currently a little bit of debate going on about the definition of nature-based solutions. I am intending to reply. I'm just trying to find the time to fit my reply in around all of the background processes of the showcase. Perfect. So, I mean, that might be a good place to start. I'll start by sharing stopping sharing the presentation so we can see the presentation, the presenters better for the Q&A session. Perfect. So, part of the debate that's going on in the chat at the moment might be a good place to start the Q&A. Is somebody has asked what definition of nature-based solution is being used here to describe the processes in this showcase.
It's the use of probiotics or microbiology bacteria to create the microbial population shift in the biological treatment plant, which already runs off bacteria anyway. That's what it is. It's a biological treatment plant. Perfect.
Thank you. I am going to try and provide a little bit more clarification for those who feel there's a different definition for nature-based solutions following this showcase. I'll reach out to you individually. Perfect. So the next question, I think might be one for you, Rob, from Amber, is there any change in gas production in the digester example?
We have not measured that because right now I believe the city of Dublin just flares that. Is that right, Michael?
You're muted.
Yes, we actually, in our anaerobic digestion on sludge, we actually use natural gas to heat. So we don't measure, the amount of gas.
Perfect. Thank you. And then another question from Amber was, what needs to change to drive selection and deselection of microbes, and how do you maintain that?
Trying to interpret that question.
I can ask for more
we-
clarification if you need it, Rob.
No, that's okay. We basically have over the years developed and acquired our own culture bank, and we know how to blend these together to achieve certain things, whether it's sludge reduction, BOD removal, control of fat soils and grease, nitrification, simultaneous nitrification, denitrification. That process is controlled through the biofermentation process, which injects the material into the plant. So we're proactively injecting certain species, all non-pathogenic organisms into the plant to create the microbial population shift. And that's simply done by pushing enough single cell bacteria of a particular type into a plant to make it dominant.
Perfect. Thank you so much. And how resilient is it to shock loads, and how long does it take to grow?
We have growth cycles within inside the biofermenter for the individual ex situ cultures. Typically, our units are designed to turn 3 times a day. Bacteria typically regenerate every 30 minutes. In the actual plant, the growth rate will be somewhat dependent on the mean cell residence time in there. But if sufficient food is available, they'll just explode into exponential growth rate until food is not available. Was there a second part to that question? Sorry. It was one on growth.
How long does it take to grow was the second part.
We grow our cultures over 24 hours and inject them in.
Perfect. Thank you. And does the microbe at all change the F to M ratio?
Good question. The way the F to M ratio is measured right now, no, because you're measuring based on mass of volatile solids. Because we increase the viability, we do say that it decreases the apparent F to M ratio, because at the end of the day, it's not about what the mass of sludge is, it's about the number of viable bacteria. You can have a bunch of bacteria in there that are not viable doing anything, and they're going to add mass to the plant. So the question is, if you increase viability and you've got 100 organisms alive and eating BOD instead of 10, has that changed the F to M ratio? In microbiological terms, yes, it has, quite significantly. But it's not changed the mass.
Perfect. Thank you. And then Oscar wanted to ask, BOD has been reduced, but are there consequences to producing double the CO2?
CO2 has to be produced somewhere. So if you put out high effluent BOD, you can pollute your river and have it produced in the river, or you can get rid of the CO2 in your plant. And on carbon measurements, the CO2 produced at source in the waste treatment system is currently exempt from the carbon accounting system.
Great. Thank you so much. And then another question from Thomas, who wanted to ask, how does biofermentation work with an MLE or EBPR process? Are there any ongoing or completed trials for this?
Yes, part of the 5-year trial was on MLE. On EBPR, I don't think that we've had any applications right now. There is no reason to think that it would interfere with phosphate removal when in conventional plants we're improving phosphate removal. At the end of the day, all these engineering separations that we try to make, that I have a special plant, is completely null and void. They're all biological plants, all of them, and they're all working with biology. We're just shifting that biology to a more desirable state and optimizing it.
Perfect. Thank you. And then Oscar wanted to ask, rather than driving selection or deselection, why not genetically engineer an ideal microbe?
Great question. 1989, Cardiff decided that genetically modified organisms were not going to be released into the environment.
Perfect. Thank you. Coming back to Amber, who wanted to ask, what impact does eliminating primary sludge from incineration on the opportunity for incineration to become autothermic?
Well, given the fact that when we get the sludge, it's 93% water, I would say you're helping the process greatly. I'd take something drier into the incinerator rather than having to go through all the drying processes first. It's just not economic.
Perfect. Thank you. And on the financial benefit side of things, which I'm going to throw open to anybody who would like to comment on this, but on the financial benefits, what is the financial payback and carbon reduction saving? What are the net carbon emissions?
I think the net carbon emissions were answered in that one slide on carbon. I think go back and refer to that. I would say that. The other part of it, because it's basically 1,000 to a 10,000th the embodied and about 500 to 1,000th of the operating carbon footprint of alternative solutions, assuming you're going to implement something rather than just pollute the river. So with respect to the costs on that, because of the changes in the carbon accounting systems in the UK and the uncertainty on whether, for example, Northern Ireland right now, I believe, is not required to pay carbon tax. And I think there's still questions arising in government. I may be wrong on this, but I think, as far as I know, the questions regarding carbon tax is still hanging out there, although I've heard numbers as high as £25 a ton.
Wow. Great, thank you. And then again, to anybody who has any kind of information they'd like to provide on this, Thomas has asked, in terms of operational complexity, how easy is it to train operators to use this technology?
Very easy, because we're not training them to use the technology. We're just expecting them to operate the system to its optimal point, and that requires doing nothing more than they should be doing normally, which is checking that they've got a blanket, checking that they have the correct RAS rates, and that they're operating at the right sludge age or the best for the plant. And we're not asking them to do anything different. This is completely transparent to the operator. I think, Michael, maybe how much of your operators been involved, Michael?
I would say they only do what they're told to do. I hate to say it that way, but when you lay down the instructions, they follow. So you can't ask for anything any better.
Great, thank you.
And I don't know if Carl's on, he'd like to comment on that too, since he had activated sludge.
Yeah, basically, you're doing your daily normal routines. The biggest thing that I noticed that you had to get out of the operator's head is the amount that they waste. They wanted to continue wasting the normal amount that they normally would, but then basically you're just putting more water into whatever you're going and not sludge. And that's the biggest thing, is just getting the mindset of changing your wasting habits.
Great.
And I'll add this also. Historically, I've tried to train the operators. They're babysitters. The bugs we use, they're the operators. Just babysit them, keep them content, and treat the amount that you're told to treat. It's very simple, and run your routine collective samples every 2 hours. That way we can measure the plant, we can measure the bugs, and we can see the results.
Perfect, thank you. I think that leads us nicely into a question from Amber again, who has asked, how do you know the right microbes are always there? What instrumentation, sampling and analysis is in place to control the process? And what interventions are needed if the population is not ideal?
They're allowed to ask compound questions. really. Sounds like a lot.
I can repeat any piece you need me to.
Yeah, I probably need it. So basically, we know the right microbes are there based on the results. The results speak for themselves. We don't have to see them. We don't have to put little flags on them. We know that they're there. Of course, you can do things like these new fancy qPCR DNA testing and all that kind of stuff. I find that of very little value whatsoever because it doesn't impact the results and it just confuses everybody. But it certainly led to a lot more research and a lot more studies. Just ask me the other couple of
no problem. What instrumentation, sampling, and analysis is in place to control the process?
Okay. Normal instrumentation is in place. If you've got DO meters and ammonia monitors, you just leave those in place. I would encourage online monitoring. I've been a big fan of online monitoring since 1985. And I think that it's useful for showing cause and effect and keeping on top of the plant. Unfortunately, with the new generation of online monitors, they're not always as reliable, apparently, as the old ones were. And then the other thing is, in terms of sampling analysis that we do as part of our turnkey service, we do check the biology on a weekly basis, and we also track viability across the plant on a routine basis using our proprietary media.
Perfect. And anybody from Northern Ireland or USA at all, have you ever had a situation where an intervention was needed if the population wasn't ideal?
I think coming down to that and the biology at Dungannon when it subject to shock loads, the interventions actually ABS were ahead of the game, as it were. The interventions happened before we got rallied round to saying this is what you need to do. You need to do something about this. The guys had already gone in there and amended it to if it needed amending in dosing terms. So yeah. So they were monitoring something to enable them to do that. I'm not a scientist, so I don't know the detail of what they were monitoring.
As John mentioned earlier about the reseeding, and we didn't do any reseeding at all during that 18-month period, as opposed to weekly reseeding, and in fact four times a week very often. Quite often a shock load would come in after a weekend, probably because the industrial body washed out their tanks or something at the weekend and hit with a big load. I would get a phone call from John quite often on a Monday morning to say the plant was beginning to go off. Can you up the dose? And in many of those times we'd already spotted it on earlier, just because we were continually monitoring even over the weekends, and we'd already started to do that, and that kept it. It never needed reseeded.
Perfect. Thank you so much. Sorry, Amber has just clarified that her question was around instrumentation, sampling and analysis was regarding the bugs, not the ASP. And does this require a weekly service/maintenance and ongoing service fee?
It is all part of our full turnkey service. We include that in everything.
Okay.
Our job, if I can just answer, I think the question's getting deeper. Our job is to manufacture microbiology and deliver a result to the customer. And that's essentially why we provide a full service, not just dumping off a bucket of freeze-dried bugs and let you throw it in if you want to throw it in. People ask oftentimes, will you sell the equipment? The answer is no. We did that before. The client doesn't have the insight to operate the equipment and maintain it in order to get the results that are going to demonstrate the cost savings. And we actually ended up buying some of our first piece of equipment back off our clients, taking back over the operation. And in fact, we have a lot of data around demonstrating, again, that the standard deviation of the final effluent quality increased from like a 3 or decreased from a 3 to a 1 when we took over the operation, and in one case put in permanent equipment instead of using demonstration equipment. So along this 25-year journey, there's been a great deal of discussion regarding that. And believe me, if we thought it would work and I could sell you a liter of material, we'd do it because it's a lot easier than providing the full turnkey service that we currently provide. But it won't work, and we won't provide something that won't work.
Perfect. Thank you, Rob.
I'm gonna go ahead and add this. I'm gonna back this up 17 years ago when I first met Rob. At that time in Dublin, we had a chemical addiction. And whenever I told the state EPD what we had, I described it as an alum addiction because the plant would not run without alum. The plant was running under compliance. I'm going to say out of compliance, because we were producing BODs and TSS 80 to 82% removal on the effluent. And we were using over 10,000 gallons of alum per month, trying to maintain a treatment that was quality enough to produce the reuse water, because we were the first reuse plant built in the state of Georgia. We were providing to a paper industry additional water for them to manufacture newspaper. The problem kept getting worse. And that's when I was introduced to Rob. He had this solution that I just couldn't believe that it was going to work. So what I did back then in 2008, I told Rob, I said, okay, you got 6 months. I'll set you up a pilot program for 6 months. Let's see what it'll do. Within 6 months, he had got us off of alum completely. And here, let me go back and say, we were using alum because ferric chloride didn't work. I tried 10 different polymers, would not work. We had to stay with alum. Within 6 months, he had got us off of the alum. Our 82% removal on BOD and TSS had increased to 95 to 97% removal. Our sludge content with that 6 months had dropped by over 60%. I knew it was working.
Amazing.
And that's the reason he's still in Dublin today. That's the reason we let him set up his lab on site, so that we could keep him close to us, so that we could make sure we continued. Our cost savings in reducing the alum to the biofermentation was over $80,000 a year. We swapped one for the other. We're still saving money.
Amazing.
The process is outstanding. And going back to one of the questions, and something I always tell people, especially my elected officials, whatever we feed this process, whatever we feed, whatever color we feed, it doesn't matter if it's red, they'll eat red. You can feed them green, they'll eat green. You can feed them yellow, they'll eat yellow. That's what's great about this process. They take care of all your needs. Shock loading, we get a lot of shock loadings because we take a lot of landfill leachate water in. These process eliminates that shock loading.
Wow, amazing.
I can't say it any better than that.
No, that's great. Thank you so much. Thank you for
In
sharing.
fact, let me go ahead and say, if Rob could qualify, he's such a great speaker, I would run him for our Congress over here just to get rid of another Democrat and get a good Republican in.
Moving swiftly onwards.
Amazing. Thank you, Michael. Great. So just a final question from Amber is, what other operational interventions were carried out in all cases? Any other kind of operational interventions that were needed and how they were addressed?
Does Dermot, you want to talk about Northern Ireland, or John, if he's still on?
No, John had to leave, but yeah, the only things that we could do was to try to optimize the plant. So you were looking at the getting rid of surplus sludges and things like that, so that you can get the age up, actually bring the total sludge production down. But they weren't what I would class as new operational changes. They were just changes that were done for the operators, knowing this is the best way to run the plant. yes, they discussed it with Rob or Connor or Sam, whoever was on site, and that gave direction to tweaking the operational plant. I suppose we did run into problems, and some of the sites can't maintain that. More to do with the reliability of mechanical, electrical equipment and things. Nothing to do with what we were doing, but it actually caused problems when we blips on the process of the plant itself, which means you don't get a perfect set of results because there's other things happening. It's a dynamic plant. Things change. That's a comment on Sam. I don't know if you want to say anything.
Oh, I sort of said it, Dermot, but yeah, at plants like Limavady, for example, which was a control plant and which gave a lot of those very good results, such as the 44% reduction in sludge, unoptimized, and all of that. But towards the end of the period, the client decided to change the diffusers in the aeration basin, and there was 2 lanes, so did one lane, did the other, and gone in and did that. Because it was a sort of an operational matter, it was actually happened, and we suddenly arrived in site to find that one lane was off. And I said to Rob at the time, this will be an interesting test to see, can we run this plant on 50% of its aeration capacity and keep it in compliance? And we did. For months. It did one lane, then they switched over and did the other one. And during those 6 weeks to 8 weeks, I can't remember the exact period of time, it stayed in compliance, apart from one point when it switched over the lanes and there was a small blip in the ammonia, but that was because the lanes were switched over and we knew what it was, and it came back within a day or day and a half. That was it. So
Perfect. Thank you, Sam. Great. And then this might be testing your memory a little bit, Rob, but what is the dose rate on the Dunmurray example, if you can remember it by heart?
I don't remember, but we dose at a higher multiplier of what we'd normally dose in the field. Of course, that might also be proprietary information because it's our internal technique.
Yeah, absolutely. If anybody wants to know the particular answer to that question, I'm sure we can find it out offline for any water companies wanting to know that information. So on the microscopic slide, did you do any microbial and filamentous analysis at all?
On that test, we were mainly concerned with the size and shape of the flock structure because we wanted to get that visual proof that the microbes were having the effect we wanted them to in the sample. So we weren't particularly concerned with things like filamentous ID. In those batch tests, you have to physically remove filamentous anyway. You're not going to see a removal during the 24 or 48-hour test. And in the full-size plant, we generally find that the microbes can outcompete filamentous regardless, so it's not particularly important to us which filaments we have.
Great, thank you, Connor. And then I think this might be our final audience question. For the change in sludge production, what was the change in the sludge age?
Kyle, are you on the call still? If so, I'll let you comment on that.
On the sludge age, I think we were running up to, in the digester, 120 something days. What made it in the digester where we actually achieved a class A here in the US for its standards is less than 1,000 mpm fecal. You had to have an 86% vector reduction to achieve class A. With that in the digester, we achieved that. The downside that we've seen with having just a traditional single digester is when you wasted any new fresh waste sludge into your digester, it shot your fecal counts up. So you would just have to manage your time on feeding your digester to keep up that fecal count, which was very manageable to do. The sludge age can vary. It just depends on if you were getting shock loads or if you take stuff that can give you a shock load. With running an older sludge age and a higher MLVSS, whenever you would get a shock load, it tended to take it a lot better and not wash your plant out just because of that higher MLVSS and your sludge age. So that was one benefactor that was really helpful that you don't see traditionally when you get shock loads at traditional plants. Here in the U.S., everything is, they have a book that we study to get our operation license, and that's what the engineers and everybody goes by. That's kind of the Bible for operations. When we did Rob, you kind of got to think out of the box a little bit. And a lot of people don't like it because you're going against what they call the traditional, operational rules. And that's the hardest thing to get people to adjust to. And, I've been away from Stark now for a little over 2 years. But I do keep in contact with them. Before I left, when I left, they quit using the ABS bugs because the engineers didn't like it. They didn't think it was worth it, and they just didn't understand it. And when I was leaving, they were building a brand new 1.25 mg AWT plant to meet the new nutrient requirements here in Florida for surface water discharging. In the 2 years that I've been gone with the other company, I think it was Woodard and Curran Engineering, it took over operations. In the last 2.5 years for the new plant got built, they have failed toxicity every single year. So they're on quarter toxicity now. Their fecal exceedances has been over the 100 on the effluent. So they've been failing that. So they're out of compliance with DEP, the Florida Department of Environmental Protection, and they got an oversight of the EPA on them right now. I just found out they just put their new plant online, the AWT plant, and they're also having to add chemicals with that AWT plant to meet the new nutrient requirements of the 321. And we were meeting their requirements with the old plant that was built in the 50s with using raw bugs without even an AWT plant. They just spent $25 million building a brand new plant, and they still have to use chemicals to make the AWT numbers, and it's ridiculous. And the cost of hauling sludge out, they're having to bring a company in to de-water and haul out, and they're paying way more money. So that goes to show you kind of what Rob and ABS can do for your plant, but you have to be willing to know that the concept works and run with it. And it's kind of the theory of doing more with doing less. And that's what we found out and start realizing. I mean, you can go into Florida DEP's website on Inoculus and look at their exceedances, which will validate what I'm saying. And you can see from the compliance that where we were making numbers and then where it changed. Like I say, it's the do more with do less kind of mentality. I mean, it works. It's been there. If I was still in Stark, we'd still be using it. No doubt. But unfortunately, things change, and I had to make a change in endeavor. But I'm still in the water and wastewater fields, and whenever people call us with the company I work for, and they're having issues, I pull them towards Rob and say, hey, reach out to ABS, and I think they can resolve your issues because unless you want to build a new plant and keep buying chemicals, you have that option, or you can go this route. And I think that's your most economical and viable route. Here in the United States, we got a saying that within the next 10 years, water and sewer rates are going to be higher than electricity cost for consumers and residents. And you've got to get that leading edge on what's going on. And I think Rob's with it. He has a leading edge of what you can do. And if you work with him, you take your knowledge that for wastewater treatment, you can better service your clientele, your people, and your environment with that, and at the cost that's not going to break the bank.
Perfect. Great, Kyle. Thank you so much. And then the final question, I think, Connor, might be one for you. In the carbon footprint, is this netted off with the increase in CO2 mentioned, and have all scopes been accounted for?
Okay, yeah. So our model was put together by URS. We later became AECOM, as Rob mentioned earlier. It's very comprehensive. It does include scope 1, 2, and 3 carbon emissions, and it's based on assumptions from DEFRA, UKWR, IPCC, defaults, and others like the Climate Registry. So it's a very good, very comprehensive model. And then in terms of the carbon increase, I think Rob mentioned earlier, it's more of a shift in where that carbon is released rather than an increase. So you're just releasing it a bit earlier in the process, and we believe that's beneficial over releasing it during downstream processing, transport, disposal. We'd love to do some more analysis on that as we go forward as well to get more robust numbers around what we're actually releasing during the process. But that's something we'll work on.
Perfect. Thank you, Connor. Any kind of final thoughts that anybody would like to add before I begin to wrap up the session at all today?
Can I just make a comment?
Yeah.
And it's to do, has been mentioned a couple of times about the digestion, and the ABS final digestion phase is not anaerobic digestion. It's a cyclic process with biofermentation as part of it, and that's what actually can make a very, very significant reduction in the sludge production. So some people think, oh, it's just doing something to anaerobic digestion. It's a slightly different process. I'd just like people to understand that.
Yeah, absolutely.
Well, I don't know if you want to mention anything on it, Rob, or happy enough.
Don't ask me to talk again, we'll be here days.
Oh, sorry, we have actually just had one more question in from Amber, who has asked, increasing the sludge age, did any of your sites move to be nitrifying from carbonaceous, which also increases NO2?
I would say yes. Crescent City was partially nitrifying before and went to fully nitrifying, and we are meeting the current total nitrogen limits, or right on the border of it. New limits for total nitrogen discharge in Florida without any engineering changes. Yes, we are aware that NOx can be increased as you produce more nitrate. And these are some of the measurements that we need to make moving forward regarding gases. Again, I will go back to what I said earlier. The nitrogen is going to go somewhere at some point. Better handle it in the treatment process. It's the most economic way forward.
Great. Thank you, Rob. So I think we'll leave the session there. Just regarding those who still have a query about the exact definition of nature-based solutions, I will reply to you individually. We just didn't have time in this to get into a deep discussion about it, but more than happy to discuss further outside of this event. Thank you to everybody again who's taken time out of their day to join us today, and thank you so much again to all of the presenters for all of your hard work that's gone into this presentation, particularly you, Rob, and Connor. Really appreciate it, and thank you for sharing the learnings so openly and honestly for those who did this project a few years ago now and have had to have a bit of a throwback. So yeah, thank you everyone, and again we'll be putting the poll to leave feedback in the chat before we end the session today, so if everybody could leave their feedback, that would be great. And with that, I'll let you all get on with your days. Thank you so much again, and bye.
Thank you.
Thanks.
Thank you, Leah.